if you look at this picture and I ask you what differentiates this object from this object, what we have never discussed up to now is if objects have some internal structure. In this representation, the fact that this node is drawn below this node doesn't mean anything. What I want to discuss now is another kind of information that we may have about nodes, which is the internal representation of a node. These items also come with no relational information. For example, if they are people, they might come with age, let's see, okay, sex, their political party, some information about their purchasing habits. But let's stick to numeric information. So age might be a number from 0 to 100, sex can be a number which is either 0 or 1. Let's imagine another pair of numbers that can represent a person. I don't know. It has very little meaning about purchasing habits, but suppose height or weight. Yearly income. They're all numbers that represent your people. Forget about relationships. All we have about our objects is a set of numbers that represent them. We call this an internal representation. Of our objects. And this representation, okay, you see, it's it's given by a tuple. And let us assume that this tuple is made of numbers. So, in general, our objects can be seen as vectors in some vector space, where n, of course, represents the number of values, the number of numbers that represent each object. It is always possible, given an internal representation, to move to an external representation. And what is a possible relationship between objects given their internal representation? For example, if we represent objects in a vector space, we can consider their distance. Okay, if we have two objects, V1 and V2, each represented by a tuple of n numbers, so actually V1 is, let's write 1, 1 up to V1n. Okay, so the vector is actually an n tuple of numbers. Okay, we can define, let's say, a distance between V1 and V2 as, for example, the common Euclidean distance, meaning the two norm of their difference. You take the sum of the squares of the difference of each corresponding component, and just to be sure, you take the square root of it. we have two dimensions, so n is equal to 2, then B1 and B2 are represented by 2 points, or 2 arrows if you prefer, in this space, and the distance between the two is exactly the distance between these 2 points. This is not the only way of computing an external representation. Suppose that we can define our numbers so that vectors B are n tuples of numbers, real numbers between -1 and 1. The age, rather than, okay, it's a real number in the reals, and you can assume that it varies actually from 0 to 80. When we want to describe our person, rather than writing directly this number, we do this. The first feature of person I, supposing that this is the age of person I, can be represented as, the age of person I minus 40 divided by 40. Since we asked this number to be between 0 and 80, this feature is between -1 and 1. We are doing some normalization of our data. Okay, the second feature, consider sex. Okay, sex, so the sex of person I is either male or female. So maybe we can say that the sex of person I, the representation of the sex of person I, suppose that we take it as the second element of the vector that represents our person, is -1 if the sex of person I is male, and +1 if is female, and so on. So suppose that we normalize every feature of each of our customers in this way. Now we have a set of values that come between -1 and +1. In this case, we have another possible measure of similarity. If you take the sex of person I and the sex of person J, this way, a measure of their similarity can be given by multiplying the two numbers. If they both have the same sex, so both are +1 or -1, their product will be 1, which can mean very similar, for example. While if they have different sexes, their product will be -1, different. So if the sex of a customer is important, this kind of product can give us information about the similarity between two people. And in general, we can define a kind of similarity between two vectors v1 and v2 in this representation to be the sum for all features of the product of the jth feature of the first person and the jth feature of the second person. This formula is actually simply the dot product of the two vectors. So if these are two vectors, v1 and v2, on a two-dimensional space, and this angle, let's call it alpha, is the angle between the two vectors, then v1 dot v2 is actually the length of v1 times the length of v2 times the cosine of the angle between the two vectors. So what you are really interested in this case, is the angle, actually the cosine of the angle between the two vectors. How do you get the cosine of the angle given the two vectors? Okay, you consider this relationship and you just move this product on the other side. So the cosine of the angle between two vectors is the dot product between the two vectors divided by the product of the sizes of the two vectors. So the two norms, of course. We are always looking at Euclidean lengths. Times this is a measure of similarity between two vectors v1 and v2. We can split this in this way. We can take v1 divided by its own two norm, dot product vector v2 divided by its two norm. So in general, our objects are vectors in Rn with arbitrary values for each coordinate. Next, we can normalize our vectors so that we can pass to vectors of features, let's call them v prime, that are obtained by the original vector of features by normalizing them. What you obtain is something that belongs to the n-dimensional sphere. Okay, all vectors have length 1, so in 2 dimensions, all vectors will lie on the circle of radius 1. This normalization allows you to compute this kind of similarity by just multiplying, computing the dot product between the two vectors without having to normalize them. They are already normalized. This kind of similarity, for this reason, is also called the cosine similarity. So at this point, we have seen two possible formulae that give us external, relationships between elements given internal representations of elements. We had Euclidean distance, where the distance between V1 and V2 is the two norm of their difference, and the cosine similarity, let's call it S, between V1 and V2, which is the dot product of the two vectors, provided that they are normalized over that. Okay. Of course, this is a distance, this is similarity. They have opposite meanings. Here, in the top case, 0 means that the two elements are as similar as possible. They are equal. While a large distance means that they are very different. In the second case, the opposite is true. 1, which is the largest value that can be achieved by this, means that the two vectors are equal. 0 means that they are orthogonal, so they don't care about each other. -1 means that they are opposite. They hate each other, in a sense. Okay. Of course, we can switch from one to the other. So, for example, if we are considering Euclidean distance and we want to get a measure of similarity, well, for example, we can define a measure of similarity, let's say S prime, between V1 and V2 by considering their Euclidean distance and maybe okay, taking the reciprocal, the opposite, okay, 1 divided by distance. This will be 0 if the distance is very large, infinite, and it will become infinite when the distance is 0. So we can easily switch from distance to similarity and the opposite. Vector spaces are not the only possible internal representation. For example, for every customer, you know which movies he already purchased. So for you, a customer I, for you, customer I is a set. The set of movies that he purchased. For example, customer 1 purchased movies 3, 7, and 10. Okay, these are movie IDs. Okay, suppose that everything can be identified by a number. While customer 2 purchased movies 4, 9, and 12. Customer 3, okay, 3, 4, and 5. And by this, you would like to build an external representation of customers, a relationship between customers. How can you do that? Well, for example, look at customers 1 and 2. What can you say about their similarity? Actually, you see, they didn't buy any common item. So probably their tastes are different. While customers 1 and 3 have some common items, 1, and customers 2 and 3 have some common item. Okay, let's put another common item between customers 2 and 3. If you want to look at the similarity between two customers, you can count the number of common items. How many movies were purchased by both customers? So, what's, for example, the similarity between customer 2 and 3? You just compute the intersection between the two sets. Of course, you're not interested in the particular items, but just the number of items, so you take the cardinality, the number of elements in the intersection. Actually, this is not enough. You can also consider the extreme case where we have two customers, let's call them C4 and C5. They just arrived, so, and they just bought one item each, for example, and they bought movie 6. With this definition, the similarity between C4 and C5 is 1. Consider this. The similarity between C2 and C3 in this context is 2, because they have two common items. While the similarity between C4 and C5 is 1, because they have one common item. Well, actually, if we look at those purchasing histories, well, you see, C4 and C5 are identical. So their similarity should be the maximum. While C2 and C3, okay, they have two common items, but they also bought some different items, for example, item 3 and item 9. So actually C2 and C3 should be less similar to each other than C4 and C5. We obtain this, okay, what is the problem here? Is the overall number of items that have been purchased. So, what we usually do is to normalize the size of the intersection, dividing it by the overall number of items bought by both customers, which is the size of their union. So if we represent our objects as sets, for example, we represent customers as sets of purchased items, then we can define a form of similarity by counting how many items have been bought by both, so the intersection, and normalize by the number of items that have been bought by either of the two customers. This kind of similarity is usually written with the symbol R prime, and it's called the Jacquard coefficient. Of the two sets. Okay, we have seen another possible internal representation of elements, of objects as sets. Actually, there is one important case where we can easily use these representations. These representations, both vector and set, come handy when you're working on documents. Suppose that your objects are documents. Documents are sequences of words, basically. So suppose that your aim is to find to tell something about sets, a set of documents. First thing that you want to do is characterize these documents as elements of some space. So either of the vector space or sets. So start from documents. Can we see documents as sets? And if so, sets of what? Well, documents usually contain words. Can we see a document as a set of words? Well, of course we can. So you can, given document, given some documents, transform each document into a set. Well, a set representation of a document is usually called a bag of words. How do you convert a document into a set? What are the steps that you need to do, starting from a document? First, you are interested in the printable words of the document. So everything that is not printable, control characters, new lines, HTML tags, if you are working with HTML and so on, can be removed. So you remove non-printable characters, non-printable items, non-printables. Second, remember that you are not interested in the relationship between words, how they are ordered and so on. You can remove punctuations. Stops, commas, columns, semicolons, and so on. So, after you do this, your document is just a sequence of words. Actually, another step, maybe you want to capitalize everything. So convert all lowercase characters, letters into uppercase letters. Because otherwise you risk to consider two words as different while they are simply, one is simply at the beginning of a phrase while the other is not. Okay, this is the easy part. Now, another important point is this. If you want to, you see, here in a set, if you have, if a word appears 100 times, you are actually collapsing these 100 instances of the word into one. You just want to see if the word belongs or does not belong to the document. Okay, this is nice, but what about different forms of the same word? So, for example, the word love and the word loves, or loved, or loving, and so on. Actually, maybe they should all be collapsed to the same word. Or all the forms of the verb to be, is, are, be, being, and so on. All of this will be collapsed to a common form, B. This particular operation is called stemming. Because you're going to find the root, the stem of the word. After this, well, we are not done. For example, there are words that are important to define a document and other words that are absolutely not important. For example, all English documents will probably contain the word the word and. So these words are completely irrelevant for our purposes of representing a document. They don't add any information about the document. And this is bad. We want to remove them. So, next step. Let's say remove stop words. Words that are too common to consider. After we have done this, we have a proper set of words that represent our document. The final step actually is more a computational one. You're not going to put the letters L, O, V, E in the representation of the document. You will build a database where log will receive a numeric ID and the document will become probably a set of numeric IDs of the terms that compose the document. So let's call this particular step, we can say it's a term indexing. I mean, as long as you keep parsing documents, every time you find a term, you add it to a collection of all terms that you have found up to now, each having its ID, maybe just its position in the list, and then this set, the set that represents the document, will actually be the list of IDs of the terms that compose the document. The document becomes actually a set of numbers. And if we do this kind of representation, we can actually, for example, given two documents, compute their similarity based on the Jacquard coefficient. Now, let's move to a different representation. Can we represent a document as a vector in a vector space? The idea is yes, by doing something very similar to what we have done before. So suppose that we do all steps up to stemming. Okay, all steps that we have seen before. After stemming, we have a list of terms that appear in the document. Suppose we also do indexing. What I mean here, how collect all different terms in all documents. We start with a collection of documents and we create, using this, a collection of terms. For example, suppose that we have two documents. The first say Alice loves Bob, and the second document says Bob hates Alice. The term collection in this case would be Alice, love, Bob. Okay, so we just examine all terms in all documents. Alice, love, Bob. Bob is already present. Hate. And Alice is already present. So the overall set of terms used in all our documents is this. By looking at all documents and building this list of terms, we can compute this quantity, let's call it Nij, defined as number of occurrences of term J in document I. Now, given this definition, we can also define the term frequency, let's call it Tf, of term J in document I as the number of appearances normalized by the size of the document. So Tfij is Nij divided by the number, the overall number of terms in the document. Overall number of terms in the document that we can define by, well, there are many ways, of course. Let's call it, okay, this set is called T, the set of terms. So we can just divide for all k from 1 to number of terms of Nij k. Or if you prefer, this can be seen as the size of document I. Okay, why do I make this normalization? Why don't I want to consider directly the number of terms, the number of appearances of term J, but I divide by the document size? Oh, because I want some good properties to be maintained by my formula. For example, okay, I want this to be a measure of the importance of term J in document I. So I want this value to be invariant with respect to maybe doubling the document. If I take the document and I write it twice, so I create a new document that is simply 2 copies of the first document. Does the term become twice as important? No, the importance should be the same. We can call this definition as term frequency. This is YTF. A document D in our set of documents becomes a vector where element of the vector is a term frequency. So we can represent document I with the vector di, which contains the term frequency of term 1 in document I, the term frequency of term 2 in document I, until the term frequency of the last term t in document I. So we actually represent the document as a tuple of real numbers. Okay, consider this document. Okay, we have Alice loves Bob, but Bob hates Alice. O and which is more common. Okay, as I said before, this word does not have it's not very important for defining the context of the document. You can expect and to appear in almost all documents. In the bag of words case, when we wanted to represent the document as a set, we just removed this word. Actually, we can do better. Since we have an idea of how many times a word appears in a document, we can evaluate the importance of a word by looking at how often it appears in documents. You can define, so if D is the set of documents, then we can define dj as the set, the subset of documents that contain the term j. So dj is subset of D, and it represents the documents that contain term j. Of course, if term j is and, then dj will be very large, possibly all of D, because almost all documents will contain and, while love maybe will be a smaller subset. So how can I represent the importance of a word? Well, I take the number of documents that I'm considering, all the documents. I divide it by the number of documents that contain j. Of course, this ratio will always be larger than 1. Okay, dj is always smaller than d because d is our universe. And it will be larger if the word is not common. So if I have few documents that contain word j, then this number will be larger. Okay. Actually, in order to contain the growth of this, we can usually take the logarithm of this. Let's say base 10, which is easier to understand. And we call this the inverse document frequency of term j, IDF, in inverse document okay. It's a frequency because it's a ratio between a subset and all documents. It's inverse because it actually reverses the usual definition of frequency. A frequency is usually size of the subset divided by the size of the universe. So this is the inverse. Because I want something that grows, that is larger, when the term is not common. And I want something that is small when the term is common. You see that if the term is so common that it appears in all documents, so that dj is equal to d, then this ratio is 1 and the logarithm becomes 0. So we end up with the so-called TF times IDF vector representation of documents, where a document is represented by a tuple with one number for each term, where each term entry is the product of the term frequency of the term within the document times the inverse document frequency of the term times IDF 2, so on, and this times IDF of the last term.